Dear colleagues, the report on the topic is offered for your attention. Application of neural networks for optimization of metal cutting parameters in AWG. Authors Oleg Rudenko, Alexander Bessonov, Oleg Ilyunin, and Natalia Serdyuk. Kharkiv, National University of Radio Electronics. The rapid development of industry and technology drives continuous improvements in material processing, aligning with the concepts of Industry 4.0. One of the most promising innovations in the sector is a press of water jet technology, where the material cutting process is powered by a high-pressure stream of water mixed with abrasive particles. The method significantly enhances cutting force and precision. A key feature of AWG is its versatility. AWG cutting be applied to a wide range of materials including glass, stone, plastics, and more. The technology high precision allows for the cutting of complex and detailed shapes, making it ideal for high precision manufacturing tasks. Advantages of AWG. Water is cheap, non-toxic, and easy to dispose of. The water jet acts as an ideal single-point cutting tool, enabling efficient automation. It can cut any contour with clean edges, allowing it to create shapes in both horizontal and vertical positions. Cutting can start in the middle of a sheet without a pivot hole. Works well with other cutting systems, expanding material range and thickness. Narrow cuts reduce waste and costs. No heat generation prevents rewelding and material degradation. Minimize fire hazards suitable for explosive environments. Prevents blade clogging in sticky materials. Fewer moving parts require less maintenance. Direct cutting force allow close edge cuts. Dust-free ideal for cutting asbestos and glass fiber insulations. AWG can cut various materials with thickness up to 140 mm for stone and 100 mm for steel. Slide 3 shows examples of AWG applications. The depth of AWG is determined by parameters such as water pressure, abrasive mass, nozzle diameter, and jet fluidity. Previous studies applied fuzzy logic and genetic algorithms to model these parameters, optimizing the process through various combinations like pressure, abrasive concentration, and nozzle speed. Further experiments with borosilicate glass showed that optimal cutting depth depends on water pressure and abrasive flow, with adjustments via advanced algorithms such as TLBO and PSO. Numerous studies have explored the effects of material properties on AWG performance. For example, both 2D and 3D processing of materials like milled steel and cast iron are consistent when parameters are properly adjusted. Parameter optimization, including surface smoothness and material removal rate, was achieved using methods like Tabuchi and ANOVA. Response surface methodology helped identify optimal conditions for minimizing surface roughness in stainless steel. Despite extensive research, no studies have focused on intelligent models for optimizing AWG cutting speed with regard to abrasive particle size and density. An important challenge is the reuse of abrasives, which maintains hardness after multiple cycles but changes in size and density. Intelligent modeling, particularly using artificial neural networks, can address this by continuously learning from data to predict the optimal cutting conditions for various materials. Artificial neural networks are increasingly applied for solving complex optimization tasks in materials processing. Their ability to model non-linear relationships between parameters and outcomes makes them highly effective. Artificial neural networks models can integrate various parameters, enhancing prediction accuracy. These models adapt to new data, learning continuously and improving the overall efficiency of the AWG process. The tool for AWG cutting of materials is a fluid jet formed in a certain way, which comes out in a special jet with a diameter of 0.08 to 2.5 mm with a supersonic speed, and provides a working pressure on the workpiece of 400 MPa and more. The liquid in the form of a jet under pressure acts on the material by area, compresses it in the direction of a jet movement, and as a result, a compaction core is formed in the material which expands perpendicular to the jet velocity vector. The laser can damage the material. Since the distance from the jet cut to the surface of the material is several millimeters, the jet pressure exceeds the strength limit of the material. Due to this, cutting is carried out. The liquid jet acts on the material similarly to a solid too. A depression is formed in the material, and if the jet is moved, a gap of a certain depth is formed, which depends both on the pressure in the jet and on the hardness of the abrasives and the strength of the material. The energy of the jet decreases with an increase in its length due to an increase in its cross-section, turbulent motion, disintegration into parts. Therefore, the nozzle tends to be brought closer to the preceded material. The general view of AWJ unit is presented in slide 6. The complex for AWJ necessarily includes a high-pressure pump, cutting head, coordinate table, and drives for moving the cutting head, hydraulic system for supplying high-pressure liquids, abrasive supply system, numeric software control system. In general, until recently, empirical AWJ models were developed based on a set of experimental data using regression analysis methods. The generalized AWJ model with a fairly high degree of confidence of experimental and model calculated data connects the process variables and is presented on slide 7. The most important variables affecting the process are cutting depth, water pressure, consumption of abrasive mass, jet speed, distance from a jet to the surface. They are shown on slide 8. To develop the model, the most important combinations of variables influencing the processes are also selected: cutting depth, water pressure, abrasive mass consumption, nozzle movement speed, distance from the nozzle to the surface, which are shown on slide 9. The slide 10 shows table 1, which shows the AWG parameters that will be included in the model. The non-efficiency parameters of constants are highlighted in gray. The most favorable conditions for effective implementation of AWG cutting can be achieved by choosing its optimal parameters: the pressure of the working fluid, the shape and diameter of the nozzle opening, the distance of nozzle from the surface to be cut, the feed rate, the number of passes material cutting is required. After transformation of equation, taking into account the values of empirical coefficient and real data, the reference calculation expression was obtained on slide 11. The general nature of the AWG process model behavior depending on the sum pairs of parameters extracted from experimental dataset is shown in the graphs on slide 12 and 13. Abrasive mass flow and fluid pressure have the greatest influence on AWG performance. The AWG process is possible when the pressure of the liquid jet per unit surface area of the cut exceeds the strength limit of the material being preceded. All things being equal, a further increase in the pressure of the liquid jet will lead to a potential increase in the thickness of the material cut in one pass. Considering an equation in general, the AWG model can be presented as follows, where according to experimental measurements, the following parameters are assumed to be conditionally constant. A pair of variables characterize the properties of abrasive particles and are present in power law form in the D parameter. Variables are present in measurements in two combinations, new abrasive and abrasive after the first cycle of use. About 1,300 measurements correspond to the first combination. Thus, using WPCA, it is possible to reduce the dimensionality of model to model, choosing the structure of the artificial neural network for N1, where N is equal to 10, the number of neurons in a hidden layer. In MATLAB 6 0.23, a number of experimental trials were performed with n number of sigmoidal activation functions, resulting in the following structure. The input values for training and testing were randomly split 70-30 and normalized. The network was trained using a backpropagation algorithm. Errors from several A and N configurations were evaluated using absolute average relative deviation, mean squared error, root mean squared error, and correlation coefficient. Optimal A and N configuration was chosen for a WJ cutting process, yielding the lowest and the highest value. Adjustments to the number of neurons or activation functions did not improve results. The developed A and N behavior is presented with three-dimensional surfaces on next slides. The production of abrasives is fairly energy-intensive, and resource-intensive production was a negative impact on the environment. The presented model implements a two-stage intelligent procedure that works with experimental data pre-processed by the PCA method and easy to debug and is aimed only at the operational assessment of the efficiency of reusing abrasives. The model can be integrated into the AWG machine control system as a software application. Optimizing AWG cutting aims to improve quality, productivity, and cost efficiency. The article presents an A&N model for identifying optimal cutting parameters, accounting for reused abrasives. The model predicts cutting speed with adequacy coefficient of 0.9891. A cost criterion is proposed for selecting optimal parameters. In the approach can be applied in software for configuring AWG units. The energy-intensive production of abrasives impacts the environment. Using a multi-objective generic algorithm, a model optimizes productivity and cost considering travel speed, abrasive mass, and standoff distance. The model is designed for evaluating abrasive reuse efficiency and can be integrated into AWG control systems. Integrating A&Ns in AWG can revolutionize the process, providing real-time predictions, improving efficiency, reducing waste, and supporting Industry 4.0 innovation. So, dear colleagues, thank you for your attention. You can see the research results in more detail in the conference printed materials.